Hello everyone, today we are going to learn about phase diagram. We have learned that phase rule. What is phase rule? In our previous lecture, it was told that what is phase rule and the specific terms that encompasses for better understanding of the phase rule. And now we are going to learn about phase diagram. Now let's take a look. What is phase diagram? A phase diagram is a plot showing the conditions of pressure and temperature under which two or more physical states can exist together in a state of dynamic equilibrium. So if you look at these diagrams, this is a diagram, this is another diagram, and this is a phase diagram, this is also a phase diagram. So phase diagram is a plot that indicates the condition of temperature and pressure, indicates the condition of temperature and pressure in which two or more phases, one, two, three, or two or more phases can exist together in a state of dynamic equilibrium. This figure shows a typical phase diagram for one component system. This diagram consists of at least three things. Number one, the regions or areas. Number two, the lines or curves. And number three, the triple point. The significant characteristics of or features of this phase diagram will be discussed later on. And before that, let me clarify these three main part of phase diagram. The regional areas. Regional area COA, this is a region, or AOC, this is a region. In the similar manner, COB, it is another region, and AOB, this is a whole region. So in this curve, we can find that it has got three regions. AOC, this is the AOC region. COB, this is another region, and AOB, this is another region. So in this curve, we have got three regions, and another component of the phase diagram is lines or curves. And you can see that there is three lines: OA, OC, OB, or you can say BO, CO, AO. These are the three lines of this phase diagram, and a triple point. And this point, this is the triple point. So let's move on discussion regarding the phase diagram. Today we are going to discuss about the phase diagram of one component system. And the one component system, the component of this system will be water, that is the water system. So from this curve, you can see that it has got all the three main features of phase diagram. It has got three areas, it has got three curves, and it has got one triple point. Okay, now what is water system curve? Water is a three-phase one component system. The total number of phases which can exist in dynamic equilibrium at any time depends on the condition of temperature and pressure. The phase diagram or pressure and temperature graph of the system, known as water ice and water vapor, is shown in the figure. The salient features of the phase diagram are listed below. Okay, it has got, I have already told you, it has got three curves, OA, OB, OC. It has got one triple point that is pointed by arrow, and the position of triple point is O. And it has got three areas, AOC, AOB, and BOC. Okay, now let's proceed to discuss the significance of each of these features. Number one was the curves, and you can see that it has got three curves, OA, OB, and OC. And each curve represents at least two phases. This is liquid water, this is ice. This is liquid, this is solid. That means the liquid water and the solid ice can coexist in dynamic equilibrium along this curve OC. Along this curve OC, in the right hand side it is liquid water, in the left hand side it is solid ice. So this curve represents two phase, and the component of this phase is water, that means H2O, and component of this phase is also water, which is H2O. That is why along is this line OC, we can say that it is a one component two phase system. Along this curve there are two phases. One phase is liquid phase of water, another is solid phase of water. So along this curve there are two phases, but the component is the same. In the similar manner, along this curve OA there are there will be also two phases. One is liquid water, another is water vapor. Liquid water and water vapor. So along this curve, both the liquid water and both the water vapor coexist in dynamic equilibrium. So curve OA represents two phase, but the component is the same, and which is H2O water. So we can say that OA curve also represents two phase but one component. So OA is also one component two phase system. In the similar manner, the curve OB, it represents two phase. That means along the curve OB, two phase can coexist in dynamic equilibrium, and the two phase is solid ice and another phase is liquid water vapor. So along OB, two phase water vapor and another phase solid ice can coexist in dynamic equilibrium. So it is also a two phase system, and the component is one, and the component is water. I have already mentioned it. So the curve OB also represents two phase one component system. Okay, the curve OA is known as the vapor pressure curve, and this curve represents vapor pressure of liquid. This is water vapor and this is liquid water, and if the liquid water crosses this line, it will be regarded as water vapor, and if the water vapor cross this line, it will be regarded as liquid water, since this region is only dedicated for liquid water, and totally this region AOB is totally dedicated for water vapor. So water, this curve OA represents the vapor pressure of liquid water at different temperature. This curve represents water vapor pressure at different temperature. Two phases, that is water, that means liquid water and water vapor, can coexist in dynamic equilibrium along this curve, and this curve ends in this point, and this point has a definite temperature and pressure value, and this point, the pressure for this point is 218 atmosphere, and the temperature for this point is 374 degrees Celsius. Okay, so we can say that the curve OA terminates at A, the critical point where the pressure and temperature I have already mentioned you 218 and 374. At this point, the liquid and water vapor are indistinguishable from each other. That means after this point, water and liquid vapor will not coexist in dynamic equilibrium. Okay, the curve OB. The curve OB is known as the sublimation curve. Sublimation means, you know that what is sublimation? Sublimation is the conversion of a solid into vapor. That means whenever any solid that converts from solid state into the vapor state is known as sublimation. And you can see that in the region BOC contains solid ice, and the region AOB contains water vapor. So if ice crosses this line, it will be automatically vaporized. It will be vaporized. So instead of going going the intermediate stage liquid, water ice of water can be sublimized by just changing its pressure. So This curve OB is regarding the sublimation of water, and this curve is known as sublimation curve. So OB shows the vapor pressure of solid ice at different temperatures. It shows the different temperature and pressure in which the vapor pressure of solid ice can be recorded. The two phases solid ice and vapor coexist in dynamic equilibrium along this curve. The curve terminates at the point B. In this point, the curve terminates, and after this point, the vapor pressure and solid ice are indistinguishable, and they do not coexist in dynamic equilibrium anymore. And the curve OC. What does it mean by the curve OC? Curve OC is the fusion curve. This is the fusion curve. Fusion means melting curve. We can specifically say melting curve. Fusion indicates that water will in the this is the ice of water which is in the solid state, and this is liquid water. If ice or ice of the water crosses this line, it will be melted, and solid ice will become liquid water. Solid ice will become liquid water. That is why the curve OC is known as fusion curve. So it depicts the effect of pressure on melting point of ice. Here ice and water coexist in dynamic equilibrium. The OC slope indicates the melting point of ice decreases with increase of pressure. If you increase the pressure, the melting point also decreases if the temperature is remains the same. That means the curve is moving in the left hand side. The left hand side, whenever the curve moves in the left hand side, that means the pressure gradually uh, indicates that the pressure gradually increases. The pressure in this point, the pressure is 1 atmosphere. This point, the pressure will be greater than 1 atmosphere, and at this point the pressure is 218 atmosphere. So the pressure gradually increases, but you can see that if we draw a line from this point to this point, you will have a value of temperature, and you can see that when the pressure was 1 atmosphere, the temperature was 0 degrees Celsius, but when the pressure is 218, if we draw a line from this point and if we land this line in this x-axis, you will find that the temperature is certainly less than 0 degrees Celsius. So if the pressure increases along OC, if the pressure increases along OC, the temperature decreases. That is why it is said that the OC slopes of the left indicates the melting point of ice decreases with the increase of pressure. So along these three curves, OA, OB, and OC, what will be the degree of freedom? And I have already mentioned that along OB, OC, and OA, there are two phases. Each and every curve contains at least two phases which are in dynamic equilibrium, and since it is one component system, the component will remain the same. Along this curve, it is two-phase system, one component, two-phase, one component system. Along this curve, it is also two-phase, one component system. Along this curve, it is also two-phase, one component system. So if we apply the phase rule, then the phase rule will become there is one component, so the value of C will be 1. I have written the value of C 1 here. Since each and every curve contains two phase, this is a phase, and these two phase coexist in dynamic equilibrium along this curve. In the similar manner, this curve also contains two phase. This is one phase, this is another phase, and these two phases coexist in dynamic equilibrium along this curve. And also this curve also contains two phase, ice phase and vapor phase. These two phases coexist in dynamic equilibrium along this curve. So each and every curve contains two phase, so the value of p is 2. We have written the value of p2 here, and applying the phase rule equation, we get that these two cancels these two, we have got only 1. That means the degree of freedom is 1. So each and every curve has only 1 degree of freedom, and this curve is univariant. This is univariant or monovariant. So you have only one option for changing either temperature or pressure. if you want that two phase will remain in dynamic equilibrium along this curve, you have only one option. You can only change either temperature or either pressure. The other thing will be automatically fixed. For example, if you want that what liquid water and water vapor will coexist in dynamic equilibrium along the curve OC, then you have to maintain, you have one choice. Since you have degree of freedom is one, you have one choice, either the temperature or the pressure. If you set the temperature should be 100 degrees Celsius, the temperature has set 100 degrees Celsius, then you have to maintain a pressure of 1 atmospheric pressure. If you set the temperature as 374 degrees Celsius, then you have to maintain 218 atmospheric pressure. Conversely, if you want to coexist, if you want to make the water and water vapor to coexist in dynamic equilibrium along this curve, you can change the pressure according to your own wish, but the temperature will be automatically fixed. For example, if you choose 1 atmospheric pressure, then you have to maintain 100 degrees Celsius temperature. You cannot change the pressure and temperature independently. We have only one independence, either temperature or pressure. That means if you choose 1 atmospheric pressure, then you must maintain 100 degrees Celsius temperature. If you choose 218 18 atmospheric pressure, you must maintain 374 degrees Celsius temperature, so that the liquid water and water vapor can coexist in dynamic equilibrium along this curve. That is why the degree of freedom has been set as 1. This thing is also true for the curve OC and also the curve OB. Okay, now let's move on the triple point. And you know that in the triple point, three phases coexist in dynamic equilibrium. In this point, there is liquid water, there is solid ice, and there is also water vapor. So three phase coexisting in one point, and the component is 1 and the component is 1. So we have got the phase rule. Now we can find out the degree of freedom. So we have got three phase at this point, so the value of P will be 3. We have written here 3, and the three phase is for the water, so the component is H2O, that is why the component is 1. So we have written 1 here, and we have got 2 from the formula. After calculation, we have got F is equal to 0. That means there is no degree of freedom and it is a non-variant system. What does it mean by non-variant system? The non-variant system indicates that you cannot change anything. You have no choice for changing the temperature, changing the pressure. You have to maintain 0.0078 degrees Celsius temperature, and you have to maintain 4.68 millimeter mercury pressure, so that the three phase can coexist in dynamic equilibrium at this point. You have two choices to change any of these factors, temperature or pressure, unless this three phase will not be in dynamic equilibrium and cannot coexist in one point. Okay, now the area, and you can see that there are three areas. I have already told you there are three areas: AOC, BOC, and AOC, BOC, and AOB. Three areas. So the area AOC represents it represents the condition for the one phase system water, that means liquid water, and the area AOB, this area, it represents the condition for one phase system water vapor, and in a similar manner the area BOC, it represents the condition for one phase system solid ice. So all this area contains only one phase. This area contains one phase. This area also contains one phase. This area also contains one phase. So we have got one phase and the component is 1. Since we are discussing about one component system, the component must be 1. So the area contains one phase and one component. Then what will be the degree of freedom? Now let's put on the values of F and C and P. In these areas we have got one phase, so the value of P will be 1. These areas called as one component, the value of C will be 1. by putting these values we got 2. That means you have got 2 degree of freedoms. You can change temperature and pressure independently irrespective of your irrespective of the boundary. So you can change temperature according to you can change pressure according to your wish, but it will remain same remain the same phase for a certain period of temperature, certain values of pressure, certain values of temperature. For example, in this point, along this point it is 4.68 millimeter mercury. If you extrapolate this curve you will have this is also 4.68 millimeter mercury, but the temperature is 100 degrees Celsius. And just after this point, in this point it might be 50 degrees Celsius. So this point has 50 degrees Celsius, this point has 100 degrees Celsius, this point has 374 degrees Celsius. All these 3 points have only one value of pressure, that is 4.68. But you can imagine that there are lots of points here, lots of points at this point. For example, this point have a pressure maybe 150. This point may have 150 degrees Celsius temperature, and it have a pressure maybe greater than 4.68. I don't know exactly what will be the pressure. This might be greater than 4.68. So this point has a value of a pressure which is greater than 4.68 and which is greater than 100 degrees Celsius. But this point has a different, this point have a different value of pressure and temperature. This point will have a different value of temperature and pressure. This point will have different value of temperature and pressure. This point also will also have different value of temperature and pressure. This point will have a value of temperature which is less than 0 degrees Celsius, and will have pressure which is below 4.68. So you can see that this whole area represents a wide range of temperature, wide range of atmospheric pressure, and it represents the temperature which is below 0 degrees Celsius and which is greater than 100 degrees Celsius. The range of temperature encompasses below 0 degrees Celsius, also encompasses greater than 100 degrees Celsius, and it also encompasses from this point to this point. It has got a different types of pressure also. So there is a lots of pressure, values of pressure, and that can be applied for this curve. But still it is water vapor, still it is water vapor. Although you have changed, you have took different types of temperature, you have taken different types of pressure, despite of your random choice, still this whole area contains only one phase, and that is water vapor. Okay, in the similar manner you can choose different types of pressure along this area. You can say that it has different types of, this point will have different value of will have a definite value of temperature and pressure. This point will have a different value of temperature and pressure. This point will have definite value of temperature and pressure, but still this area contains only one phase, that is water, that means liquid water. In the similar manner, likewise the previous two one, this area also contains only one phase, and you have got the independence. You are independent of for choosing the temperature and pressure. You can choose the pressure as 1.5 atmosphere, and you can choose a different value of temperature which is less than 0 degree or greater than 0 degree. Still it will be, it will be in the solid state. So in the area you have you have a freedom to choose the temperature and pressure independently. They will not depend on each other. But in case of curve you have only one choice. You can choose independently, you can choose only the either the temperature or the pressure. If you choose temperature, then the pressure will be automatically fixed along the curve. I am talking about the curve. If you choose the pressure, the temperature will be automatically fixed. But in case of area, you can choose different types of pressure, different types of temperature, and still the area will represent the phase that is allocated for that area. Okay, so the area is bivariant. We have got this area is bivariant, curve is monovariant, and triple point is non-variant. Now what is metastable equilibrium? You can see that in the phase diagram there is a dot line that indicates a metastable equilibrium. Meta is a Greek word which indicates that which is movable. Anything that moves is known as meta, and stable means that do not moves. So this word metastable is quite confusing. Metastable curve indicates that although the vapor pressure curve of OA can be extrapolated as OA prime. What does it say? The vapor pressure curve AO terminates at point O. AO terminates at the point O. When the liquid freezes or solidifies, and after O, if you extrapolate the curve, this is the area where the solid ice should remain. That is why if we come in this area, you will find that this area contains only the solid ice. But by careful cooling of the liquid under conditions that crystals do not form, the AO curve can be extended to A prime. In that case, this state is called supercooled state. The supercooled liquid is in an unstable condition. On a slightest disturbance, the entire liquid solidifies rapidly, and the dashed curve OA prime represents a metastable equilibrium. What does it mean? It means that generally AO is the curve that will terminate at the point O. That will terminate at the point O. After termination, if we come in this area is dedicated for solid ice, and you will find a solid ice in this area. But if we cool the liquid water very carefully, then the water will not solidify. That means the water will not be converted into solid ice. Instead of converting solid ice, it will remain the liquid, but the temperature will be as like the solid ice. That means the temperature of the liquid water will be below 0 degrees Celsius, but it is not solid ice. It is still the liquid water. And if it disturbs this liquid water, if we shake this liquid water, which is uh, very much which is supposed to be solid ice, if we shake this liquid water, which is cooled at the point below the point of point of freezing point, still it is not frozen, it is not solid ice, still it remains in the liquid state, then we will draw a curve which will be like this, and we will call this curve as metastable equilibrium. We will call this curve as metastable equilibrium curve. Metastable equilibrium curve. Why we are calling this metastable equilibrium? Since it is not sustainable. If we slightly disturb this liquid, if you shake this liquid, then this liquid will rapidly solidified into solid solidified into ice. It will rapidly solidify into ice. That is why this curve will not be a real curve, and it stays for a very short period of time. That is why we are calling this a metastable equilibrium. Okay, let me state this again. Suppose you have got a liquid and you are cooling this liquid, and you have already decreased the temperature below the 0 degree Celsius. Below the 0 degree Celsius, the liquid should become solid solid ice. The liquid water should become solid ice, but you have cooled the liquid very carefully, so the water is not has not become solid ice. Instead of becoming solid ice, it is remaining in its liquid state. But if it slightly shakes the liquid, which is remaining in the liquid state below 0 degree Celsius temperature, then after shaking, the liquid will become solid ice. Since the liquid stays for a very short period of time, so we have put this condition in the curve as dot line, and we are calling this condition as a metastable condition, and we are calling this curve OA prime as metastable equilibrium. Okay. In the metastable equilibrium, there will be supercooled liquid and vapor, which will be in dynamic equilibrium. Okay. Now we can see that in the water system there is also a curve which is represented by wave prime, and this in this time it is written here supercooling. Supercooling, that means it is liquid but it is below 0 degree Celsius. It is staying liquid, it is still liquid at this point, which is certainly below 0 degree Celsius. And below the 0 degree Celsius this liquid should be in the solid ice state. Instead of being solid ice state, it is maintaining its liquid state. That is why we are calling this super cooled water. Super cooled water, but this condition is very unstable, and if you shake this water, then this water will rapidly solidify and will become solid ice. That is why we are calling this a metastable equilibrium. The vapor pressure curve AO can be continued beyond the triple point O as shown by the dashed wave prime, that is water can be supercooled. The supercooled water remains in equilibrium with the water vapor, and it is known as water vapor system, which is unstable. And once you shake this water, it will rapidly solidify and will become solid ice. Then the curve will disappear from this plot, and we will then call this ice and vapor equilibrium. Okay, now take a look. Now let's take a quick look at the sulfur system. The sulfur system is also one component system. It has got four phases. The four phases are two solid phase. This solid phase indicates number one rhombic sulfur, number two monoclinic sulfur. There is liquid phase, which is known as liquid sulfur, and one is vapor phase, which is known as sulfur vapor. The rhombic sulfur, the two crystalline form of sulfur, rhombic sulfur and monoclinic sulfur, can interchange with each other at a temperature of 95.6 degrees Celsius, and you can see that the rhombic sulfur converts into monoclinic sulfur by absorbing when you heat this at 95.61 degrees Celsius, and this monoclinic sulfur will become liquid sulfur if we further heat this monoclinic sulfur and increase the temperature at 120 degrees Celsius. And after getting the liquid sulfur, if we cool this liquid sulfur, it will first become monoclinic sulfur, and if we further cool this monoclinic sulfur, it will become rhombic sulfur. So it is a temperature that converts the rhombic sulfur, one crystalline form of sulfur, into another crystalline form of sulfur, which is known as monoclinic sulfur, at 95.6 degrees Celsius. And this temperature, at this temperature, they show enantiotropy. Rhombic sulfur and monoclinic sulfur exhibits enantiotropy. Enantiotropy indicates that the temperature that converts one crystalline form into another crystalline form. Okay, now let's take a look about the sulfur system. You can see that the sulfur system contains four phases: A, B, C, D. A, B, C, D. This is a curve. And like the other phase diagram, it will contain. Let me say this first. The phase diagram must contain curves. It will contain area, and it will also contain triple point. And now let's find out the area of sulfur system. The area A, B, C, D. This is the area. This area is dedicated for sulfur vapor. This contains only one phase. Another area A, B, E, G. This is another area. This area is dedicated for solid rhombic sulfur. Let's take a look at another area D, C, E, G. This area is dedicated for liquid sulfur. This area is dedicated for liquid sulfur. And B, C, E. This area B, C, E, or conversely you can say that B, E, C. This area is dedicated for monoclinic sulfur. So we have got four areas in sulfur system curve. It will also contain the lines or curves. So it has got one line AB. Along this line, the rhombic sulfur and sulfur vapor, exist in dynamic equilibrium. There is another line BC. Along this line, monoclinic sulfur monoclinic sulfur and sulfur vapor, they will remain in dynamic equilibrium. It is this line represents two phase one component, that means one component two phase. The line CD, along this line the liquid sulfur and sulfur vapor exist in dynamic equilibrium. It is also one component two phase system. The line CE, along this line the monoclinic sulfur and liquid sulfur exist in dynamic equilibrium. It is also one component two phase system. The line EG, along this line the solid rhombic sulfur and sulfur liquid exist in dynamic equilibrium. It is also one component two phase system. The line EB, or you can say that GB, along this line the rhombic sulfur and monoclinic sulfur exist in dynamic equilibrium. So we have got how many lines? 1, 2, 3, 4, 5 and 6. It has got 6 lines. It has got 4 area, 1, 2, 3, 4 area and 6 line, and it has got 3 triple point B, where rhombic sulfur, monoclinic sulfur and sulfur vapor, this three phase remains in dynamic equilibrium. Triple point C, in this point the liquid sulfur, sulfur vapor and monoclinic sulfur will exist in dynamic equilibrium. And triple point E, where the rhombic sulfur, liquid sulfur and monoclinic sulfur will remain in dynamic equilibrium. So that's all about the sulfur system. I've already told you it has got 6 carb, 3 triple point and 4 areas. Okay, so that's all about sulfur system. And like every like the previous water system phase diagram for water system, the sulfur system will also have different types of degrees of freedom. The triple point will have no degree of freedom, triple point will have no degree of freedom, and the area will have 2 degree of freedom, and the line or curve will have 1 degree of freedom. Okay, that's all for this moment.